Okay, Assalamualaikum dan salam sejahtera. Today I would like to cover some topic regarding heat exchanger. This is tutorial on heat exchanger actually. So basically, uh, we have here a parallel flow heat exchanger and also counter flow heat exchanger. So if you want to know which one to manage which one, actually you have to draw whatever the heat exchanger look like. For example, here we have a parallel flow, so we know that this hot fluid is coming in from this direction and also cold fluid coming in at the same direction. So this is parallel flow. So T1 is whatever the first flow means TH in minus TC out. Also T2 is equal to whatever higher minus lowest TH out minus TC out. So you got delta T1 and delta T2. So by having delta T1 and delta T2 plug into TLMTD or T-log mean temperature difference, you got delta T1 minus delta T2 over log delta T1 over delta T2. So you got TLMTD. So if you have a counter flow heat exchanger, so means that in this reverse direction. So you have here, for example, you have a hot fluid going in these directions, but you have the cold fluid is going out at that direction. So this is delta T1 actually, TH1 TH in minus TC out the delta T1, and then you have another one is delta T2 is TH out minus TC in. So you got delta T2 over here. So if you compare this both a bit different, so don't remember, just draw and you know this is delta T1 and delta T2. So that's one is regarding TLMTD, okay, basically. So here we have another one that this is multiple pass. Besides having TLMTD is straight direction, so somehow in design they have a multiple pass and also correction factor for a multiple pass. So they just time whatever they have TLMTD by F. This is a correction factor. So how to get this F? Yes, time the F. So here if you have for this formula, Q equal to UAS, supposed to be QAS delta LMTD. So just time F if they have a correction factor for multi-pass and cross flow. Okay, how does the multi-pass and cross flow look like that? If you like to find the F, the value of F. So here is example. If for example here we have one shell pass out, here we have T1 and T2 and E1 also T2. Big T means the T that fluid that going in outer shell. This is inner shell, inner tubes, and also T small and T1 small, T2 small is for the inner tube, and big T is for the shell. So this is other design. For example, we have two shell pass, and here we have only two tubes actually. Sorry, 4 tubes. 2 shell pass, 4, 8 and 12. So actually just look by the figure, because the figure is we could determine whether this is which figure to refer. Okay, so let's have a look on the example. Okay, so this is example not regarding the above one, but most likely could enhance your knowledge. So here we have a steams going in and steam going out. Down there we have cooling waters coming in. So here you need to determine the mass flow rates of the cooling water needed, and also mass the rate of condensation of the steams in the condenser. Okay. By knowing this is heat exchanger, so you need to calculate delta T1 and delta T2. So here we got heat and also 16, and we got TLMTD is equal to 11.5. Then by using the formulas, Q equal to this is equal Q equal to delta U AS TLMTD, and we got final answer is 1087 kilowatts. Okay. And mass flow rate of the cooling water is equal to M. It's actually rearrange the formula here. Q dot equal to MCP delta T. Rearrange it, bring out the M, so we got it Q over CP delta T, and we got this value 32.5. And also for the steam, just using this formula, Q equal to M dot HFG, so M dot for steam equal to Q, the same Q actually, so just over HFG is equal to 0.45. Alright, let's have a look on this one we will done in the class. So means in the slide in the lecture note. Okay, so let's have a look on the similar parts regarding what we discussed just now, the correction factor. Okay, but have a look on this figure. This is if I go back, this is similar to this one, correction factor, to this figure. So we have 2 and also 2 big T and so 2 small t. Here we have 2 shell, one shell over here and so one shell over there. So here we have T1 going in and going out, going in, so going out. So we have actually 4 inner tubes, right? So by referring on that, actually here you need the questions given that we have a hot waters from 80 degree going to this heat exchanger, and then we have a cold glycerin 20 degree, and also try to cool down this hot waters. So how to solve this one? What is the questions? Questions mean determine the rate of heat transfer in the heat exchanger before any fouling, and also after fouling factor of 0.006. This is given occurs. So you need to find the Q dot. Okay, and given here we have a convection heat transfer coefficient here 2.25 watt per meter and glycerin on the glycerin side, and 160 watt per meter on the tube side. So first and foremost, what you need to do, what we need to do, try by having whatever data that we have. So here the first thing, we know that we want to find the Q dot. So bring out the Q dot formula first. This is the way that we try to find out how to find what are the parameters that we need to find later on. So by having this formula, Q dot equal to UAS F delta TLMTD. This is F we have here because this is correction factor. So it needs U, it needs A, it needs F and TLMTD. So first of all, it needs what we calculate is here we could calculate A. AS. So AS equal to pi dl equal to pi 0.02 times 60. So we got 3.77 meters square. And then we need to calculate, here we need to calculate U and also to find the F. So first and foremost, try to find the, we could find U first. U is equal to 1 over, U is overall heat transfer coefficient, is equal to 1 over R. U is equal to 1 over R, so R is equal to 1 over Hi plus 1 over Ho. This is R actually. Okay. If you remember, U is equal to 1 over R. R total. So R is equal to what? R is equal to, this is the formula that you have. 1 over Hi plus 1 over Ho. R total. R total. This is U actually. So U is equal to 21.6 watts meter square Kelvin. Okay, and you got U over there. Next, you try to find what's this value of F. Here from the figure, try compare which one is T1, which one is T2. So here we got, this is formula is actually from the graph. This formula is from the graph. Okay, so compare with the one that you have above, and you got this answer 0.065 and 0.075. And from the graph, you would have that F equal to 0.91. So let's have a look on the graph. Here, for example, you have this is R. R is blue line. So which one is R? R is equal to, sorry, I don't remember it. R equal to 0.75. Jump down. 0.75. 0.75. The other one is P is equal to 0.67. Okay, let's have a look on R first. R equal to 0.5, 0.75, 0.75. 0.75 is somehow here. Alright, then it have P is equal to 0.6, 0.67. So if I draw this thing, 0.75, 0.75, 0.75, 0.8, 0. Okay, maybe this is 0.75. This is R, and you have another one. You have value of P 0.67, 0.67, 0.65, 67. This one. So here you got value of P over there, 0.9 something. Okay, 0.91, 92. That is quotient factor of it, 0.91 or 0.92. Okay, 0.91. And then by having this one, you already have then you need to calculate TLMTD. Okay? TLMTD is delta T1 minus delta T2, and you got 24.7. And plug in everything, you got Q equal to 1830 watts. Okay, the next question is after fouling factor. what is fouling factor? Fouling factor means that you have some debris mungkin karat ke benda ke dalam tu lah yang menyebabkan dia komponen yang melekat pada dinding menyebabkan ada fouling factor pada dinding, menyebabkan kadar sepatutnya lebih rendah Q itu lebih rendah. So it has fouling factor 0.006. So dekat mana letak dia? Actually you need to put in the formula R. So R total awak berubah R total berubah, R total awak akan jadi this one this is fouling factor 1 over H1 plus 1 over HO plus RF. So RF has been given, so you got everything 1 over R equal to 21.3. Plug in everything back, everything is the same, only U is different, so you got 1805. So by comparing, you know that when you have a fouling factor, actually it will reduce the heat transfer rate. Okay, so that's why refrigerants you need to make it the cylinder is very clear without any fouling factors and doing maintenance, because you reduce the flow rates, reduce the flow rate and also reduce the heat transfer rate. Okay, thank you very much.